holds an Ontario professional engineering license, and is currently undertaking his MBA through Ohio University. Andrew has been with TRC for 3 years, and in addition to overseeing the facilities and security departments, leads all large capital projects, including the Smart Center. Welcome, Andrew.
Thank you. Thank you. You never quite know what you're getting into when you're asked to come out to one of these events. So, I chose a topic that I thought was pretty relevant here. I wanted to focus on the Smart Center traffic control system, knowing that some of you at least will be traffic engineers. Hopefully the rest of you will find this interesting as well. Hopefully all of you have heard about Transportation Research Center. We've been around for a long time, since the early 70s. We're certainly one of the main driving factors attracting the automotive industry to Ohio. We're very proud of that heritage. We've been a long-time partner of the Ohio Department of Transportation. Nick mentioned a number of the recent wins for both of our organizations, and we're happy to be a part of all of those. So a little bit more about TRC itself. Of course, we provide services to the entire mobility industry. So we test passenger vehicles, trucks, commercial vehicles, off-road, military, motorcycle, ATVs, UTVs, basically anything that has wheels, maybe tracks as well, we test it. We also, of course, get into now automated and connected vehicles as well. That really gives kind of a quick introduction. I wasn't going to spend a lot of time on TRC itself. I wanted to spend a little bit more time on the technical aspects. So what is the Smart Center? Well, first off, Smart Center, of course, is an acronym like everything that we do. So the Smart Mobility Advanced Research and Test Center is a $45 million project currently under construction at TRC. We received funding through ODOT, Jobs Ohio, and the Ohio State University. We're very happy to partner with those companies. Very happy to receive funding through them as well. That's a big part of what made this project possible. The facility itself was developed, the concept was developed over about 5 years. We had a number of meetings with different stakeholders, OEMs, technology companies, as well as NHTSA, so other governing agencies, to develop a concept that we think is unique, but also complementary to what else is available in the market. And so what's the function? Well, the function is to provide a closed course, safe, controlled environment, repeatable, for doing automated connected vehicle testing and development. A couple of the photos there at the bottom show how far we've come. That photo on the left, that's a lane following system. That photo is circa 1974. Ohio State research project, trying to follow magnetic lines or magnetic strips in the lane. That was the best way they could think of doing it. Up top, to the right, we're showing kind of a more advanced system. This is production ready. This is level 2 type systems, crash imminent braking, trying to make sure you don't crash into the person in front of you. This is an overview of TRC itself. It's very large, 4,500 acres in East Liberty, Ohio. That's about 40 minutes northwest from here, along US 33. So go onto the US 33 connected vehicle corridor, go right past connected Marysville, and you'll end up at TRC. So an absolutely massive area. Some of the key features are shown here. The biggest being a 7.5 mile oval or a high-speed test track. We have a 50-acre vehicle dynamics area, a skid pad that's 9,000 feet long, 6-lane wide, a variety of handling courses, bump courses, emissions lab, full vehicle crash lab, and then the newest feature of the Smart Center there, which is overlaid in black. The Smart Center itself is roughly 540 acres of greenfield development within our existing proving ground. So looking at some of the particular features of the Smart Center, anything kind of shown digitally here is new and overlaid. The first being an intersection, which is 6 lanes wide. North to south is roughly 1.2 miles long. I don't think you get a lot of private institutions kind of constructing their own highway on their private ground, but that's what we've done here. The other two features, or the other features there, are also a control building, which houses all of our coordination and control for the site. An urban area, which is still under construction, and I'll show you some status on that, and a second vehicle dynamics area. So the urban area here, of course, like any construction project, this photo's a week and a half old and already outdated. We have lots of paving going on at site. Actually, all of the surface there that's shown, kind of, you can tell the outlines of the facility. That's already received 2 lifts of base course asphalt. So we're well on our way to completing paving on this area later this month. Vehicle dynamics area is a little bit farther behind. This is a 450-foot wide, 2,000-foot long, so that's about 21 acres of new pavement. We're about a third. So about a third of it has base course of paving on it, about a third has stone right now, and a third is curing from its cement stabilization. But we're very excited. We're hoping that the weather holds for us this fall. We had an awful spring, as I'm sure any of you in construction know. It was slow and rainy and wet, and not a lot could happen, but we've had a good fall so far. So if temperatures stay good, we're going to get this completed this year. If not, we may have a little bit of paving to do in the spring. The other nice feature here is the control room. We constructed about a 10,000 square foot new building. It houses 4 private use work bays for our customers to come in. That allows them to stage their vehicles. They can prepare. They can do recalibrations of their vehicles and come in between tests and do checks. It also houses our advanced mobility group, which is one of our pillars within TRC. That's the main focus of automated and connected vehicles. So some of those grants that TRC's worked on with ODOT, a lot of that work came through the advanced mobility group. There's a photo of our control room. Certainly not quite as grandiose as some of the DOTs might have, or even some of the municipalities. But considering we're really controlling, just a handful of intersections, it's more than sufficient. Very nice place for us to operate. Also a nice place for our customers to monitor testing. The control building, of course, kind of serves as the hub for any of the network and controls throughout the facility. So we have a direct line of sight out into the main intersection, helping with some of that coordination and control, but then also they can view any of the cameras throughout the site to help. So that kind of gets us to the main part that I want to talk about today, which is the traffic control system. So that means something a little bit different to me than it might mean to you. TRC historically has been focused on the automobile itself. We produce facilities, we have test labs, but really we're worried about helping our customers achieve their goals by testing full vehicles. A lot of that's durability, performance, compliance testing. So we hadn't really had to worry too much about being traffic engineers or traffic controllers. In fact, a proving ground, if you look at a typical proving ground design, in a lot of cases we're trying to eliminate the number of intersections so we don't have vehicles possibly interacting. Loops, turnarounds, big open pads, yes, intersections not so much. So as part of the Smart Center, we needed to develop a traffic control system specifically for this facility. So for us, that was a big package that included signalized intersection, all the above ground structure signals, detection controllers, power and fiber distribution throughout the site, wireless communication systems, and some of the control room equipment and software. And I'll detail each one of these. But we spent a lot of time thinking about what were the fundamental goals of this system. And for us, there was a number of key goals. One being replicate typical intersections. So how do we replicate something that's as close to the real world that an automated or connected vehicle might encounter, but still safe, controlled, repeatable, all the main goals of the facility itself. We also needed to be able to have a huge amount of flexibility. So we could create a very simple 4x4 intersection and have it statically fixed, and that's great. That might serve 1% of our test needs. What happens when a customer comes in and they say, yep, okay, we tested that, we're happy. We're happy with that configuration, we don't have any problems. That's fine. We do have a lot of customers that come back and say, well, actually, I was driving in Indiana in the middle of nowhere, and I came across this intersection, and I had 2 right-hand turn lanes and a left-hand turn lane, and I had a flashing yellow arrow, and our system had no idea what to do with it. So we went back to our original request for proposal and said, how do we achieve that goal? How do we make something practical, but that we can also go back and change based on our customer requirements? The other part of it was, how do we simulate things like failed systems? I'm sure all of your traffic engineers will tell me, well, no, traffic controllers don't fail. We know it happens every now and then. With level 4 and level 5 automated systems, we have to really test for every possible scenario. And then how do we coordinate all these different systems in and amongst themselves, and how do we coordinate them with some of our test equipment as well? One more thing, I'm showing a scenario here. I just want you to keep this in mind as we're going through. This is I would call it a typical scenario, test scenario. Generic, it's not any of our customers, we made it up, but it's very similar to what some of our customers might do. You're actually seeing the red arrow there. That's a guided soft target, so that's actually a surrogate vehicle. It's a foam car on a robotic platform. It's approaching an intersection and it's seeing a red light. There's north and south traffic, which you're seeing there in green, and another vehicle approaching from the east, which is also seeing a red light, but it intends to turn right. This is an everyday scenario, but this is something just to keep in mind as kind of we're going through some of the systems here. So the intersection itself, it starts off fairly conventional. It's a box layout, double span wire, but fairly large, 132 feet pole to pole. We have actually 4 signal heads per direction with 5 lights per signal. A little bit of an interesting geometry there. We ended up having to use an ODOT size 14, which I think is the largest standard traffic pole you can buy. After that, you get into custom sizes. We've also installed some crash attenuators, a little bit different. We're trying to keep infrastructure as far off the roadway as possible, leave lots of room for runoff for any of our test systems, and then, if something were to happen, how do we make sure that we lessen the impact of that type of incident? With this, we essentially are reconfiguring the intersection as needed. The signage is magnetically affixed, some of the overhead, so we can quickly swap those on and off. We can change the light configurations, and we can quickly put down temporary markings. So if we want to change the right-hand lane to a dedicated right-hand turn only, we can do that. We want to add left or left-hand turn lanes, we can do that as well. If we want to completely shut down lanes, we can do that too. So certainly not a standard intersection. This is just a nice overhead shot showing the intersection there. And again, this is kind of midway through that scenario. So I'll show you a video of what happens here. But you can see some of that overhead signage, some of the striping. This was a little bit near the end of construction, so not all the striping was in place, but gives some bounds to the intersection and shows some of the size. We recognized that there was enough complexity here that we needed to develop a tool. How do we tell our customers and even our internal stakeholders how to configure this intersection for any given test? So we came up with a system. This is really trying to describe all the different possible configurations of signage, light configurations, pavement markers into a graphical form. You'll notice a ring structure in the middle there, so something to essentially discuss with our customers when we say, what do you want us to set up for your particular test? You'll also see on the right some of our signal heads. You'll see something very unique, which is we have 2 different arrows pointing different directions. So again, that lane assignment, we may actually change that from a right-hand turn to a left-hand turn. So that's why we ended up with 5 section heads. We have yellow arrows, green arrows, and sometimes 2 facing the opposite direction. So I think by now, hopefully, any of your traffic engineers aren't cringing at me yet and saying you're breaking all of the rules of standard traffic control. Don't worry, we'll make it even worse for you. So we have a brand new advanced traffic controller cabinet. I'd like to say we hopefully have the most advanced intersection, in North America right now. Certainly our partners have come forth to us with the most advanced technology that's currently available on the market or brand new to the market. So we're using, Cobalt controller, That new ATCC allowed us to use high-density switchbacks. We're using all 32 channels of switchbacks. And what that gets us is individual control of each light segment. So I said, we can come up with different scenarios. That means down to the individual light. We can put on, red and green at the same time. We can do a Christmas tree arrangement, if you will. We can do failed systems, so turn off the light completely. Yellow and red scenarios for European type signal operation. Any of those configurations are possible. We've actually come up with a programmable conflict monitor to remove any of those conflicts, and then also a separate controller, which I'll keep the details for now, but essentially a separate controller that we've called pinball mode that allows us to completely bypass the controller itself, the traffic controller itself, and go directly to the high-density switchbacks. Something that, configurations you just cannot do with a typical traffic controller. We're also we've kind of installed a good deal of traffic detection here as well. So we have 4 autoscope vision detectors, 4 AccuScan radar detectors, and 36 in-ground magnetic detection sensors. So I'm sure a lot of this is pretty familiar for a lot of you, autoscope vision with an advance and a stop bar detection. This is fairly conventional. The big difference for us is that we are not using this as a static configuration, we're changing this all the time. So if someone wants to set up a scenario where they actually want the lights to trigger based on a vehicle at 100 feet away from the intersection, we'll redraw the boxes for that particular test and or come back. So this is kind of the default for us, showing the 4 directions, but it's changed quite frequently. This is probably a little less familiar. This is from the radar traffic detection. So again, it has about 1,000-foot detection range. We've drawn some detection boxes there. This is actually one of our asphalt trucks passing through the intersection itself. It gives us a vehicle classification as well as speed count. A very interesting additional data for us. Now, we don't have a lot of traffic out on the facility. We know what's out there, so some of that statistics really isn't that useful to us. We might use it in the next year and say, oh yeah, we had 1,000 vehicles pass through the intersection, but we're not going to get the big volumes. Mostly what we're using it for is to help set up the scenario and drive the inputs for the test that we're looking to do. And then also some of these pucks as well. That's what our graphic looks like. Nick did a great job talking about some of the connected vehicle applications. TRC is a little bit technology agnostic in this space. We recognize both 5G and DSRC are suitable technologies, but we also recognize that we need to have both. Our customers are coming in, we have a wide variety of customers coming in, and they may ask for very different types of tests. So we've gone out and, again, we've tried to install the most current technology, what's out now, but also keep in mind what's our flexibility for in the next 5 years when we potentially need to change the technology. So right now we actually have site-wide coverage of DSRC and cellular V2X, as well as a site-wide Wi-Fi system. So that's using 6 CAPS dual-band RSUs, so these are brand new. These have both the DSRC and cellular V2X or 5G application on them. We're using 6 Danlaw onboard units. Those are really just for us to have in stock for any of our customer use. So they may come in, not have an onboard unit of their own, but want to test a connected vehicle application. So we have those on the shelf for our customers to use. We also went ahead and invested in a system called Fluid Mesh. This is actually a high-speed Wi-Fi system that's designed for trains. So they've tested it up to 250 kilometers per hour. This allows us to live data stream off of the vehicle while it's in motion at excessive speeds. We have a number of different applications for that, one of them being onboard video live streaming. So say we have automated or even non-automated vehicles, we can now install multiple onboard cameras and actually live stream that data back to the control room itself. It helps us kind of monitor if we're doing safety driving remotely. The other one is really just offloading data. We might have automated or connected vehicles that are generating huge amounts of data, especially from things like LiDAR sensors, their onboard cameras, and other types of analytics. And instead of storing all that data locally on the vehicle, we're able to offload that to the control room and provide that to our customers or for our own use. We're also working with Verizon to install a 5G node, so more of a conventional cellular 5G node at the intersection. We're one of their kind of first partner sites, recognizing that this has a lot of good use for helping sell the technology, honestly, to different automotive companies. So in order to support all this equipment, we needed to put in our own infrastructure. We were basically constructing our own small city, 540-acre city. It was a greenfield site, so we needed to put in all the power and network infrastructure to support this. So we have something in the order of magnitude of 4 miles of underground conduits, utilizing some of that multi-path fiber conduit, and then some conventional conduit as well. We actually had some difficulties. We wanted to stay away from doing a lot of high voltage power distribution. So we have mostly a 480 volt power distribution with local transformation down to 120 volt. One location that was still too far, we really couldn't make the math work. So we adopted a solar and wind solution there. So that one's running on 48 volt. Seems to be working pretty well for our application. It looks a little bit like what some of the ODOT weather stations look like, that's for sure. What you're seeing on the right is actually some of our one of our network diagrams. So this is a schematic view of the fiber distribution throughout the site. So basically everything is a private network back to our control building. We have kind of Cisco switches in the control building, and then Moxa field switches out in a lot of these different equipment cabinets. So one of the photos there is a typical stand on what we have that has power, fiber, and then that's where we're installing any of our DSRCs and other connected vehicle equipment. This also allows us some general locations where we can provide power to test equipment on an as-needed basis. Some other features, I have one non-photo for you, a schematic. They were installing the weather station yesterday, so I didn't have a chance to upload the photo to it, but we have a Visala road weather station. We went pretty full out on that one. We actually have temperature, humidity, wind speed and direction, solar intensity, present weather, road temperature, and road surface state. A little bit different application than what ODOT would be doing. We're not necessarily providing this information to help the drivers drive safely or let them know about poor weather conditions. We want to know what the conditions were when a vehicle came out to test. We have a lot of customers who are worried about how vehicle perception systems will be able to read signs or traffic signals when the sun is low in the sky. Backlighting systems. So to be able to actually measure what the solar intensity was at that time is key. We get a lot of fog at TRC, so we do know that there's a lot of customers who want to come out and actually test in some of those inclement weather. So being able to actually characterize and quantify what level of fog or snow or rain was happening at the time of that test is a critical thing for us to monitor. We also have a closed caption television system for the site. It's so big you can't see it from one location. So we have 12 cameras, including 2 of those are pan-tilt zooms that allow us to monitor the entire site from a couple of fixed locations. All this data, all these systems have to be pulled together. Luckily we're a single site, so we're utilizing our own private network and bringing all this data into a common workstation. Monitored, logged, and pulled together. But, I understand it's a little bit of a microcosm of what you guys are trying to do with data across the state. So I can understand the challenges that you must have. We have one location, and still it's certainly a challenge to pull all this data together. So one of the other big investments as part of the project is the actual test equipment to support. This type of equipment's still pretty new in the market. It's in that 3 to 4 years old, and is extremely expensive. We've spending on the order over $3 million in various test equipment just to support our customers in testing on the site. So what does that look like, or what types of equipment did we need? SSV is strikeable surrogate vehicle, which is the image on the left. It looks like the back of a Ford Fiesta, but made out of carbon fiber. It's on a rail system. There's a number of different types of targets. Guided soft target with robotic platform, different types of pedestrian targets. You'll see a deer there. We like to call that the European deer. He's only about this tall. Certainly not an Ohio deer. Children, the robotic platforms to put those pedestrians on. Certainly some temporary structures and barriers, construction barrels, sea containers to replicate buildings, brake, throttle, and steering robots. So that's actually to actuate the test vehicle itself. So taking some of the driver out of the loop and actually pre-programming those maneuvers, brake thresholds, what's the steering angle, what's the steering rate. Portable traffic signals, so we invested in 4 portable traffic signals with its own DSRC roadside unit. So those can be used to set up temporary intersections at our facility, can be used off-site or in other test features at TRC. That allow us to do things that are a little bit weird geometry. Everyone has an intersection in their town that's something of the odd variety. And in Marysville, we have 5 points, which is a 5-way intersection. There's certainly no way we were going to construct a 5-way intersection and pave that and build that. The costs are too great. So instead, what we do is we use some of our very large asphalt pads. We'll do temporary striping. We use the temporary and portable signals to set up what that configuration and still be able to test what it looks like. Also a lot of data acquisition systems and even having some of our own vehicles to test. How do you make sure these systems are working properly and your test scenarios are working? You can validate your test systems. We actually had to go out and purchase some of our own level 2 automated vehicles rather than relying on renting them or other aspects. So what are the use cases here? Why did we do all of this? What are our customers asking us to do? What are our partners asking us to do? The first one is maybe a little bit more straightforward, validation of advanced driver assistance systems. Now that's a very broad label for crash imminent braking, lane keep assist. There's as many acronyms and different titles for each of those. That's the one area where we're starting to see some standardization. So new car assessment programs, there's actually now a few standard test procedures for some of those systems, but there's still a huge amount of variation across manufacturers and across implementation. So just because you buy a lane keep assist system from manufacturer 1 does not mean it's going to have the same features or perform the same as manufacturer 2. So a lot of the work that's going on here right now is evaluation of current systems and development of those next generation ones. One of the second applications here is development and validation of connected vehicle applications. So there's a lot of promise in the connected vehicle world, a lot of ability in what we can do with those connected vehicle signals, but how do you validate that before you actually deploy it on a public road? We know you probably don't want to go and close an intersection to go do some tests. So this is an ideal location. We have the closed course environment, the tools already available where that type of connected vehicle application can actually be tested before deployment. Pre-deployment of infrastructure technology, so same thing. If there's a new piece of traffic detection system, traffic controller, it's an ideal environment for plugging that in, safe. You're not going to have the general public coming through the intersection and being your test case. We can provide some of that test traffic itself. And then, of course, the future really is testing of highly automated vehicles. So really letting some of these level 4 and level 5 vehicles loose out on the facility, testing how they actually perform, where are the hiccups, what validations need to be done before they can be released, how can improvements be made to these types of systems. So coming back to that original scenario, now that you know everything that we have, the capabilities, the systems in place, put yourself in our shoes. How did we come up with this scenario? What is it testing? How did we set this up? So we knew what we wanted to do ahead of time. We wanted this vehicle to run red light. We knew that. So we chose a guided soft target as our application. So this has a robotic platform underneath of it. The robotic platform you can actually pre-program a GPS path. We want it to go through the intersection at a particular speed, changing speed, lane changes, whatever we're looking for. In this case, fairly straightforward in that we wanted to go straight through, ignore the fact that there's a red light. We use a guided soft target because if it's struck, it's a foam car. It's not doing damage to the vehicle that struck it. It's not potentially harming occupants. It's the safe way of doing things. We never use real vehicles or real personnel in any of our tests other than behind the wheel itself. The other traffic in there, that's again some of our test drivers. So we've told them, we want you to provide a little bit of kind of obstruction traffic. So this is just, general traffic going north-south. They have a green light. They're permitted to do so. Drive as if you were driving in the regular world. And a vehicle coming down and turning right. What you don't see off screen here is there's another vehicle coming from the north. This vehicle is traveling fairly high rate of speed. Let's call it within the speed limit. But, he has a green light and is obscured by a forested area, or it could be a building, from seeing that potential red light runner. So how did we set this up? Well, we pre-programmed the light signals. We actually shut off the stop time, and we just forced it into green light north-south and red light east-west. We said, we don't care. It doesn't need to change ever during this test scenario. That makes it a lot easier for us. But we could have set it up to trigger such that, it showed a red light, particularly to that guided soft target based on some sort of external input. We also didn't implement in this case, but we very well could have implemented some of the vehicle-to-infrastructure, vehicle-to-vehicle applications of a red light runner. So that would have provided more information to the systems, to the driver itself, but we wanted this to be, a blind test. You had no other information other than what the vehicle could perceive. We wanted to be able to record the vehicle parameters and onboard footage. We wanted to be able to stream that data back to the control room live, and we wanted to be able to sync the cameras, traffic control, weather data all together into one scenario. So what does that look like? I'll let it play through one more time with a little bit of voiceover on it. But you can see essentially it's an avoidance maneuver, red light runner at the last minute. Now what I will tell you in this case is that the vehicle is not doing that on its own. The vehicle would apply brakes on its own, but the swerving maneuver was completed by our driver. But this is exactly the type of scenario that we would be looking for a vehicle to be able to react and do this type of avoidance maneuver itself. It's just not currently available on the market. So that's all I had for today. I certainly have a couple minutes for questions if anyone has any. I know we covered a lot of content there. Okay, well, thank you very much, and thank you for having me.